If that's what you need to keep the light bulb fresh, make sure you prioritize it, because your mental health is just as important as your study health.
George back for some more MCAT podcast. How you doing, my friend?
Always great to be here.
I don't know about always great. This biochem section is destroying me, destroying my confidence and my knowledge, and destroying my score. To boot.
No, not at all. This is honestly where the practice is like the best place to make mistakes, because it doesn't matter. No one's gonna look at it. No one cares, right? Just a little bit of fun.
My ego cares. And I mean, I'm just only putting this out for the world to see that Dr. Gray has forgotten all of this stuff. So anyway. It's funny. There's that TikTok trend going around of like, as a anesthesiologist, here are 5 things I will never do. As a trauma surgeon, here are 5 things I will never do. And I'm just like, as a doctor podcaster here, I don't really have any trend to go there. Anyway, so again, we've talked a lot of mindset stuff. Really struggling here, making sure that we stay on track. We don't overburden our brain with negative self-talk. We get to another passage. Take a deep breath, close eyes, say some prayers. Is that the general thought?
I think even if we take a step further back, there are times throughout our prep where it feels like, concepts aren't sticking, or maybe it's discouraging, because it's like you feel like you've put in a lot of work. A lot of the students we see for their first, 1, 2, 3 full lengths, to be like, I feel like I'm not seeing progress. I feel like I'm plateauing. And a couple of things to remember there is that, each full length is going to cover, like the MCAT, if everything that the MCAT can cover, they're only going to cover a small section on a full length, and another small section on your next one, another one. It's not until your later ones, until you really start seeing things over and over, that things start to overlap, right? Most students in their prep see the largest score increases at the tail end of their prep, which is hard to think about, because you're like, I just want to see the progress now, right? Yeah. But what it really comes down to, again, is that it is easy to get discouraged, but that's why it's so important to reach out and get like a good social network. It's really important to plan your breaks, to make sure that, if you're like, I'm going to be disciplined in my study for 2, 3, 4 hours a day, but I'm also going to be disciplined with my time off, right? If my time off is going out with my friends, or like going for a run, I'm going to watch the sunrise, the sunset, whatever it may be, going to the gym. If that's what you need to keep the light bulb fresh, make sure you prioritize it, because your mental health is just as important as your study health, right? Like they go hand in hand. If you feel like you're burning out and you're staring at the page, the words are there, but they're not going in. Granted, there are some things that you have to prioritize, in the sense that, okay, like I came out once this week, I won't go out 5 times a week, but still plan those things. Look forward to those things. They'll keep you going, right? They'll keep you fresh. They'll keep you invigorated and ready to study for the MCAT, versus like burying your head in a book for 8 hours every day, and like you lose track of time. You don't know what's going on. You're not seeing your progress. And then it's just a downward spiral. So find ways to lift yourself up when those things are down, so you can keep yourself going.
Yeah. All right. Speaking of keeping ourselves going, Let's talk about passage 4, Biochem from Blueprint MCAT Diagnostic. Again, everyone gets the Diagnostic for free over at blueprintmcat.com, signing up for that free account. Let's go and jump in.
I'm going to warn you, this is a tougher passage, but like, again, this is where the structural understanding can really help. So let's dive into it. Passage number 4. The quality of DNA-labeled affinity probes is critical in DNA-assisted protein analyses, such as proximity ligation assays, PLA, and immuno-PCR. Efficient, high-performance methods are therefore required for isolation of pure conjugates from reactions where DNA strands have been coupled to antibodies or recombinant affinity reagents. An important step in the synthesis of these molecules is sequentially removing any unconjugated affinity reagents and remaining free oligonucleotides from conjugation reactions as shown in figure 1. So let's just take a step back here, right? alphabet soup, a lot of words in here, a lot of concepts. Like you might be the listeners being like, well, what did he just say? What did he say? Right? So this is again where it's, remember, a lot of this stuff is presented as background. Do we need to know all of it immediately? Do we need to know all the techniques? Probably not. If it's important, it will be expanded on. So I look at this and I'm like, okay, we're talking a little bit about quality of affinity probes, something about isolation. I kind of lock into this here. There's a need, right? So efficient high performance methods are required for what? Isolation of pure conjugates. I might highlight that. I'm like, this seems like the goal of whatever we might read. And ultimately, this comes back in that final sentence. It says, removing any unconjugated affinity reagents and remaining free oligonucleotides. So this makes sense. We're isolating something. We're trying to wash away the impurities. We want something specific. We're probably going to see some methods, right? If we come towards this next figure, I look at this, and quite frankly, my first reaction is like, okay, sick. Like there's some steps. This is the illustration of the purification process. There's no, like, I'm looking for the clues that can give me hints. I'm looking for in the caption if they're going to describe anything more about it, about like step A is, step B is, step C, nothing. All it says is figure 1, illustration of purification of affinity binder oligonucleotide conjugates. This is probably like the methods, but I'm not going to spend too much time on it because if it's important, they'll explain it. Sure enough, the next paragraph. First, so now we're going to methods, right? First, the conjugation is performed in solution by mixing antibodies with an excess of azide-modified oligonucleotides. The resulting mix containing antibody DNA conjugates and remaining free antibodies and oligonucleotides is incubated, and the products are immobilized on agarose beads. After washes to remove unconjugated antibodies, the captured antibody DNA conjugates, along with unconjugated oligonucleotides, are both released by enzymatic cleavage using the restriction enzyme MLY1 that cleaves at the border of the complementary region, figure 2, between the capture and the conjugate oligonucleotides to release single-stranded DNA-coupled conjugates. The cleavage process requires both ATP and S-adenosyl L-met in order to run to completion. The eluate was then captured on protein G beads, and washes were conducted to remove any free nucleotides having no antibodies attached. Finally, purified conjugates were eluted from the protein G beads by lowering the pH. A lot of steps, but for me, this is, again, don't get lost in the details. For me, I'm somehow trying to relate this paragraph, because really it's a bunch of methods. All I'm trying to think of is this is a bunch of methods. And I see this methods and I say, this relates to my figure. This is the story that describes the figure that I just saw. So making that kind of link, I'm not going to get too caught up in all of the specifics, but I might try to see what happens at each stage. I know ultimately I'm working with oligonucleotides. So like a strand of, DNA building blocks, right? Oligonucleotides. I'm also working with some sort of conjugate. Something's going to attach to it. So I might highlight even first. First, there's some sort of conjugation. So first, highlight conjugation, antibodies, and oligonucleotides. I know that at my first stage, I'm going to take my strands of DNA, I'm going to conjugate it with something. Okay. The next process, there's going to be something that happens. There's like a mix, great, fine. They're immobilized and washed. Okay, so I would highlight immobilized and then washed. Then I know the function is we're removing something. We're washing, we're getting rid of something right after it says removed unconjugated antibodies. I'll just keep that in the back of my mind. I'm going to highlight immobilized and washed. From there, what happens? There's a step of enzymatic cleavage. Something is released. So I might highlight enzymatic cleavage. I'm again trying to orient myself to the stages that I do know, the stages that I recognize, right? Getting rid of the fluff. It could be A, B, C, D for all I care. I'm just trying to orient myself to the steps. So enzymatic cleavage. And ultimately, this cleavage is going to do something. It's going to cleave somewhere. It's going to release DNA-coupled conjugates. Okay, so now I'm starting to build a picture. There's some conjugated, some unconjugated. We want this idea of purity. So I'm going to highlight release DNA-coupled conjugates. We're just trying to follow the process. And then this cleavage requires some things. I'm just going to remember that. I'm not going to highlight necessarily. And then ultimately, it was captured on this other thing, conducted. Oh, I'm removing free oligonucleotides. I might highlight remove free oligonucleotides. What are we left with? Purified conjugates, and then a final step, lowering the pH. Interesting. So by orienting myself around the steps, I'm really focusing on just the steps. I don't need to worry too much about what's happening in the middle. If somehow I need to relate it, I'll come back to this figure, I'll come back to this paragraph, and I'll tie it all together. But remember, you're only rewarded for understanding as far as the questions ask you. So now we're down to figure 2, right? We see these 2 strands of DNA, we see some sequences, and figure 2 says enzymatic cleavage by our enzyme. Cool. Just some sequence. Maybe we're asked about complementary sequences. I'm thinking MCAT testable content. Not going to spend too much time here. And final paragraph, these purified high-grade probes extend the capabilities of traditional immunoassays to allow direct detection of proteins and modifications with high specificity and sensitivity. With them, designated protein targets can be readily detected and localized with single molecule resolution and objectively quantified in unmodified cells and tissues. Really, all I get from here is the author saying, this method is great. We ultimately get what we're looking for. Again, that purified idea of probes, high-grade probes, immunoassays. I might just highlight maybe high sensitivity, high specificity, just to get an idea. And they're talking about, single molecule resolution. The point here is they're saying this method is great. Okay. We described all the methods. This method is great. So with that in mind, I would be ready to approach the questions and maybe come back to see if there's anything that I actually need from the passage. Let's have a look. Yeah. How do you feel? Like this is again.
I feel like I haven't read anything and now I'm going into these questions.
Oh man. But remember, sometimes the questions like pseudo-discretes, maybe it's a super intimidating passage. And this is why you have to keep in mind, you're like, okay, I'm going to take what I know. Even if I don't know anything, I'm going to try the questions and I'll come back if I need it. That's the right approach because they will throw big, ugly things at you intended to scare you. But the mindset of, I'm just going to take like one step at a time. I'm going to read the question. I'm going to figure out what I need. If I don't know, I'm going to move on. If I do know, fantastic. Right? So let's try it out.
Okay. Whatever you say, George. Question 19. In vitro, free oligonucleotides such as mRNA transcripts have a short half-life in the cytosol. What mechanism is used to stabilize these molecules? So this doesn't seem like it has anything to do with the passage.
There you go. It's pseudo-discrete, right? Like again, we talked about oligonucleotides. It's from the passage. It's a buzzword. But do you need any information from the passage here? No. This is why it helps. Like you could spend 5 minutes just your head buried in your hands. And you're like, oh, like I don't understand. And you see a question like this, and you're like, hey, this is just some basic like biochemistry, central dogma stuff. Like I should know this, right? Go right into it. That's why it helps not to be fazed by these big, ugly passages. They will throw it at you specifically to throw you off your game. Remember that these questions exist. Mm-hmm. These are common on the MCAT. A lot of people are like, oh, it's not going to be that easy. It is. There are tons of questions like this where they give you a tough passage and you still have to, it's like a pseudo-discrete. If you know the content, you can answer the question.
Yeah. So the rephrasing this is basically saying, how do I stabilize oligonucleotides such as mRNA, right? So they don't get stabilized. To me is so they don't get degraded. And so answer choice C to me seems dumb, right? I don't want to digest something if I want to stabilize it. So I'm going to get rid of C. Active transport across the nuclear membrane. Well, it's telling me how do I stabilize it in the cytosol. So I can't really transport it if I want it there to use. I need to stabilize it. And so I'm left with A and B. Phosphorylation, polyadenylation. Phosphorylation always seems like it's like the answer to everything. It's in every answer choice. Polyadenylation sounds like it's fun, so I'm going to go with A just because I'm tired of phosphorylation being an answer.
So I want to begin by saying I loved the paraphrase. That was fantastic because again, you're taking like a longer, and a lot of these questions can get really long. I love the paraphrase where you said, all I need here is what makes oligonucleotides stable? What makes mRNA stable? Meaning what prevents degradation? Mm-hmm. Fantastic. The first step is figuring out what you need to answer, right? And that was perfect. Your logic on eliminating C, fantastic, right? Enzyme digestion, you're breaking it down. No, that's what we want to prevent, right? Mm-hmm. C is eliminated. D, active transport across the nuclear membrane, just like you said. You want it in the cytosol. Why would you transport it? D is incorrect. So A and B. A is the correct answer. So excellent. So let's actually break this down, right? So Phosphorylation, you're right. It happens all the time. You stick a phosphate on, you take a phosphate on. ATP is everywhere. You stick a phosphate on, taking a phosphate off. Like, it's coupled to a lot of reactions. It's a very important process. A ton of proteins are phosphorylated, dephosphorylated. Like, that's a whole like turning on, turning off mechanism. But in this case, we're talking about mRNA or oligonucleotides. The mRNA is the example that they gave us. When we think about transcription in our cells, the biggest things is we think of post-transcriptional modification. So if we think of like an mRNA transcript, if we want to stabilize the transcript, we need to make modifications to this transcript to stabilize it, right? This is called the post-transcriptional modifications. And there's two big ones. This might ring some bells for people at home. It might ring some bells for you, but the poly A tail and like the G, I think it's like the G7 cap, like the G cap. There's a G cap and a poly A tail. And basically you stick these on. These are post-transcriptional modifications that are slapped onto your mRNA, which is an oligonucleotide, to stabilize it, right? So polyadenylation, adding many. So poly, many, adenyl groups, so adenine, right? Polyadenylation is a poly A tail. You're adding that poly A tail to stabilize the transcript. A is the correct answer. So phosphorylation is involved in a lot of regulatory pathways for turning on and turning off proteins. In this case, we want to stabilize oligonucleotides. A is the best answer.
Okay.
Yeah.
I got it.
Great. So question 20. Given the locations of the MLY1 cleavage site and recognition sequence, MLY1 is not a what? A, type 1 restriction enzyme. B, type 2 restriction enzyme. C, type 3 restriction enzyme. D, type 4 restriction enzyme.
Yeah, so this is again straight up, seems like straight up pseudo discrete. Like, we didn't talk about restriction enzymes anywhere, I don't remember, especially type 1 through 4. We did talk about in the question, right, this MLY 1, and we have the figure 2 here talking about it, where it is. So I like, obviously, I like talking about thought process on these questions, and sometimes I don't have anything to go off of a thought process on. There's literally no thought process that I can do here. So if a student is in this situation, is this one where it's like, don't waste your time, pick C and move on, or whatever you want? Okay, I'm going to pick C. Type 3.
Amazing. The correct answer here is A. The correct answer is A. But I 100% agree with you. I read this question when I was like prepping as well, like looking over these slides, and I was like, I don't know. Like, this, it's a very discrete content nugget. Like, we talk about enzyme sites and restriction enzymes. It was briefly mentioned in the passage, like MLY1 is a restriction enzyme, but this is such a specific thing where there really is no strategy. It's like a pick your favorite number, right? But the point is, like, 1, never leave a question blank. 2, like, guess and move on. Don't give it extra time. This is one of those questions that you could stare at for 5 minutes and you still have no extra information, right? So just like you did, pick your favorite number and move on. Mm-hmm. In terms of the actual content, this comes down to, well, if we look at figure 2, and this was also new to me, but if we look at figure 2, it shows that the cleavage site is super close to the recognition site. Now, a lot of enzymes will sometimes have the cleavage site within. So like, they recognize this part, they're going to cut within the same area. Sometimes it's very close by, and sometimes they bind one place, they recognize one place, but then they cut at a much further site. So the distinction here, and honestly, I would say this is definitely not a question you should kick yourself over, because this is a very, very low yield, discrete, like minute detail. If anything, I would say of all your full lengths, all of your AMC stuff, every practice question that you do between now and your test date, you're going to see like a maximum of one more question like this, if any. So this is why we also focus on strategy, not so much content. You're never going to see another question that asks you word for word type 1, 2, 3, 4 enzymes again. But for the sake of completeness, let's talk about type 1 enzymes, right? Type 1 enzymes is correct because the idea is we are also looking for not, right? MLY1 is not what? Type 1 enzymes are specific in the sense that they recognize a certain site and they cut somewhere very far away. If we look at figure 2, we can see that just downstream or very close to our recognition site is our cut site. That does not satisfy our need for a type 1 restriction enzyme. Therefore, MLY1 is not a type 1 restriction enzyme. Type 2 restriction enzymes are considered anything that cleaves within or like short distances of your sequence site. So this would be fine, right? The cleavage site is very close. Type 3, they require like, they also same thing, can be a short distance or close by, but they do require this S-adenosyl L-methionine thing, which was mentioned briefly in the passage. Again, very discrete content. And then D, type 4 are enzymes that target like modified DNA, so methylated versus demethylated or hydroxymethylated. We don't really get any information for figure 2 here, but you could reason out that if there's a cytosine, you could slap on a methyl group, or like you could modify this DNA if that event was there. So maybe you could say it'd be a type 4, which is least correct, which is it not for sure. It can definitely not be a type 1 because by definition, a type 1 says the recognition site is very far away from the cleavage site. We see from figure 2, they're actually quite close. So this is, again, very specific knowledge, but one where it's like pick your favorite number and move on.
Yeah. Okay. Yeah. And this was a not. You got to make sure you make sure you keep that straight in your head as you're going through.
For sure.
All right. Question 21. Which nucleophile was likely used to prepare the oligonucleotides used in the purification procedure? Sodium hydroxide. Is that how you say that one? A?
Yeah.
Sodium hydroxide. B, CH33, CCl. C, HCN. Or D, sodium nitrate? Nitrate? What's that one?
That would be I can't give you all the names because there's a few here. So we have NaOH, CH3, 3, CCl,
yep.
HCN, NaN3. So there's a reason I'm not giving you the names because there is like, it is an expectation to know the nomenclature, but it's also, there is a very fine trick to this question. But if you do know certain names, maybe you can eliminate. So first, think like, would you be able to answer this question without passage information? Are you expected to know how oligonucleotides are modified or purified? Are you expected to know that?
I don't know.
The answer is no. Yeah, in this specific case, the answer is no.
Yeah.
So if you're not expected to know it, this is one of those where you can probably find it where?
In the passage.
Yeah.
So we talked about this whole this whole second paragraph here, all of these steps that are happening. I'm assuming the answer is somewhere here. Which nucleophile? Oh man, George, help me out.
All right. Do you want a hint?
I want the answer.
I can't give you the answer.
That's all the people want. Give the people what they want, George.
So I love that you're thinking about nucleophile, but also think about what the nucleophile is involved in. What is it doing? So use the question to guide yourself. What is it doing? And look for where it's being done in the steps that we laid out. In short, what are we doing here? What is the nucleophile doing?
Purifying.
Even a step before that. The entire process is purifying, but what specifically is it doing? What step? Because the entire method is the purification. Mm-hmm. What specific step? What is the nucleophile actually doing, given in our question?
I don't know. It's preparing the oligonucleotide.
So where do you think that would occur? We did see oligonucleotides. Mm-hmm. And if we're looking for prepare the oligonucleotides, in another way, this is saying like, modifying oligonucleotides, changing, like modifying, if we look at our steps, do we see somewhere where we are preparing things? Preparing also suggests what? You think early or later? Early. Okay. Do you see a step where you have prepared or changed oligonucleotides?
The beginning part. You're conjugating antibodies with oligonucleotides. Mm-hmm.
And what about those oligonucleotides?
Azide modified.
There it is. So now the question is, do you know which one is an azide group? Right. And see if you can use process of elimination.
Yeah, I don't remember.
Yeah. But walk us through. Let's talk about A. What, like you said, what is the name of that guy?
Sodium hydroxide.
Is there an azide in that? Any sodium hydroxide, azide?
No.
No,
I don't.
get rid of it. It's not it. B, do you see anything in there that might be azide?
What's an
Possibly.
azide again for the listener? Not for
I
me,
can't.
because
I
I know
can't
what
tell
it
you. I
is.
can't tell you. Not just quite yet. Not quite yet. But in this, like B is kind of like CH3. 3 is like a trimethyl chloride here. This wouldn't be an azide. C is hydrocyanide. So CN, the CN group is a cyanide group. Sorry, I think it's a nitrile group. No. Ooh, what is it? It's not. It's not an azide. Yeah, sorry.
Okay.
I'd have to double check. It's either a hydrocyanide or it's a nitrile. I think it's called a nitrile group. So
Okay.
in this point, the C is triple bonded to the N, and then there's an H at the end. But this is also not an azide. An azide is an ion where it's N3 minus. N3 minus. So sodium azide, which is what we would see at the bottom here, NaN3. This would be sodium plus an ion with N3 minus. This would be sodium azide. So if we're talking about specific steps, like which nucleophile is likely used to prepare the oligonucleotides. Again, the strategy is, what am I looking for? I'm looking for something that prepared the oligonucleotides. I knew I had all these steps, prepares kind of early. I'm looking for something that modified oligonucleotides. The keywords in the passage here was azide modified oligonucleotides. If we know azide, now we're going to look for something azide. We're saying that's not a sodium hydroxide. That's not some sort of trimethyl chloride. That's not, hydrocyanide. And then we end up with, by process of elimination, sodium, like azide here. So NaN3. Tough question. Yeah, tough question.
Lots
but
of
do you also see up to this point, have we used the passage a whole lot? No. And this is the teaching point, as in they will throw you this big ugly thing. You can spend forever trying to figure it out. But if they don't ask you a question about it, it doesn't matter, right? So let's take a look at this again. So some proteins and antibodies are susceptible to pH damage. In order to prevent this damage, what would be the most efficient and effective additional step to perform at the end of the elution process? A, adding 0.1 molar glycine HCl, pH 3, or B, 0.1 molar NaCl, pH 7, or C, 1 molar tris hydro HCl, pH of 8.5, or D, 0.7 molar potassium hydroxide, pH 13.85. So again, we're talking steps. Where would you look if you're thinking steps?
Back to this middle paragraph. Going back to the steps. The elute. There's the elute. We have elution process. Finally, the purified conjugates were eluted from the protein G beads by lowering the pH. So if they're lowering the pH, it's saying some proteins and antibodies are susceptible to pH damage. In order to prevent this damage, what would be the most efficient and effective additional step? So if we're going to lower the pH to elute from the protein G beads and we want to protect, it seems like we would want to add something basic if we're going to make something acidic to protect whatever it is that we're doing. So D is the most basic at pH of 13.85. So that's the one that I would jump to. But then I'm confused of 1 molar versus 0.7 molar. And is this a stronger acid or base or whatever? Yeah. What do you think?
What's your final answer?
I think D.
Sure. Your thought project, so everything up to that point was perfection. In the sense that you said, okay, listen, I'm talking about the methods again. I'm going to go to the passage. I'm going to find the steps. It says additional step at the end of the elution process. I'm scanning. Oh, finally, they were eluted. This sounds kind of like the final step. What additional step? What would I do after? And you said the immediate step before. They lowered the pH. They made it more acidic. We probably want to counteract that. We're going to add something more basic. You're absolutely correct. So we can narrow it down to C and D. Now, my question is, the first part of the question says some proteins are very susceptible to pH damage. Which one is more basic, just based on the solution? So I'm going to tell you right now that the reason that it says pH 8.5 and pH 13.85, that's telling you the pH of the solution. Which one is the stronger base here?
I don't remember.
So which one's more basic, though? Which one's more basic, just based on the pHs?
D.
D is more basic.
Yeah.
So if D is more basic, and remember, it's very susceptible to pH change. If we want to, because we still do need to lower the pH to kind of elute it out, right? It's a necessary step. We just want to prevent an overshoot. If you want to prevent an overshoot, do you want to add, kind of a weak base to offset the acid, or a really strong base to offset the acid?
Well, the way that you're asking that question and how I read the beginning was some proteins and antibodies are susceptible to low pH damage. So I immediately assumed high pH, that's not going to matter, but it just says pH damage in general. So we don't want to go to the extremes. We want to play in the middle somehow.
That's exactly it. C is the correct answer, right? So in this case, everything up to that point, you're absolutely correct. You're like, okay, we want to lower the pH because that's what's in our final step. So to counteract that, we want to prevent too much acidity. We want to prevent acid-caused damage. We're going to add a little bit of base. How much base? We want to add the weaker base because we want to prevent the overshoot. We don't want to shoot it back up and turn it back into a basic solution, super basic, because that can also cause damage, right?
Yeah.
Too much base can also cause damage, just the same way that very little or too much acid can. You think of corrosive materials, you can have very corrosive acids and also very corrosive basic solutions as well. So that would be the correct answer. C, 1 molar tris HCl. The contents of the specific solution in this question honestly don't matter. It's very specifically the pH here. We're adding something basic, slightly basic, to make it slightly less acidic to prevent damage. That's really all you need from this question.
As our good friend Megan Trainor says, it's all about that base.
All about that base.
All right. So
I really liked your thought. So even though we didn't get the right answer there, your thought process was perfect. The approach was perfect. The fact that it was in that last bit and you're I'm just going to go with the bigger number.
Yeah,
it's totally fine. The extra step at the end is you don't want to overshoot, right?
Yeah.
So it makes sense to take the more mild one. But excellent. So final question.
All right.
Which step of the procedure corresponds to the release of DNA-coupled conjugates? Is it, I'm not even going to read the A, B, C, D, because it's step B, C, E, or D.
Yeah, and so we're going up to figure 1, which is where all of the drawings are showing things going on. And so we see A, B, C, D, E, F. We only have 4 of those 6. Which step of the procedure corresponds to the release of DNA-coupled conjugates? So if we look, an important step in the synthesis, blah, blah, blah. An important step in the synthesis of these molecules is sequentially removing any unconjugated affinity reagents and remaining free oligonucleotides, blah, blah, blah. I don't know. What is it doing? So we have the illustration of purification of affinity binder oligonucleotide conjugates. So we have DNA. I'm assuming what we have here, the little line is either DNA or an oligonucleotide. And they're conjugated together. They're hanging out together. Which step of the procedure corresponds to the release of DNA-coupled conjugates? Jeez Louise. What is going on? So the only I don't. It's D. The answer choice is D. That's correct. That's what I'm going with, because so and there was logic there, right? So I look at B and I go, okay, I don't really see what's going on with B other than this like, I don't know, structure on the left comes in. I have no idea what the structure on the left is. And then so that's B. C is, okay, I don't see anything changing between C and B other than, I don't know, there's this one thing that floats off in space. So I'm not sure what's going on there. Some sort of cleavage happening, something going on. I don't know. Answer choice E, like, I don't know. There's this other thing, like things are just popping back in here. Something's happening. The only thing where I see a release of anything is from this thing on the top right to this thing on the bottom left, which is D. So I'm like, this has got to be it, because I don't see anything else going on.
And honestly, that's perfection. Like, it's perfect. That's really all it is. I think, like, for the sake of completeness, it's really helpful sometimes when I'm reading the passage, because I was looking that you were looking in paragraph 1 for your answer.
Yeah.
This is where sometimes it can help to have that kind of structural idea in mind. Paragraph 1 says, we have a process to purify some target. And start to finish, this is what we do. We remove the unconjugated affinity reagents. We want to remove the, the remaining free oligonucleotides. We want to end up with what we want, our pure conjugate. So this is, again, the introduction and the start and finish. The next paragraph is all the steps, right? The first this happens, then that happens, then we wash, then finally this, that. So that's where, if this question is asking about steps, that's where we want to look. And really, the second paragraph here, from the first to the finally, this paragraph is all about describing that exact figure. The figure is a diagrammatic representation of the process, but then everything in this section here talks about that figure. So this is also what I meant by sometimes, like, you look at a figure and the figure can be very informative. Other times you can look at a figure and it really doesn't tell you anything, and it's probably going to be expanded upon in the actual passage. So just like you highlighted here, you noticed released DNA coupled conjugates, right? If we want to look for a cause and effect, we're going to see, okay, well, something released these DNA coupled conjugates. I'm scanning before that. What happens before that? Enzymatic cleavage, directly before enzymatic cleavage. So if we return back to our diagram and we try to infer what's happening, this is exactly what we see in step D, right? In step C, we've added this enzyme, and the little lines you see is the cleavage site where we're cutting things. So you can notice that in D, they're a little bit shorter. You're left with the region that's been, like, after you remove things, this is the region that's left. This is after you've snipped it, right? So D is the correct answer. D is the stage where the enzyme is added to kind of cleave things off. In step C, for the sake of completeness, kind of like you mentioned, you see, all I see is this random, this little thing, like, it's being taken away. Step C is actually, if we look even in our paragraph, this is the wash step. The wash so after it says after washes to remove unconjugated antibodies, that's that step right there. We washed away the unconjugated antibodies. And now it makes sense. These little Y things are antibodies. These little lines are our oligonucleotides. The conjugated antibody oligonucleotide complex is when they're attached together. So we can see that at step D, you have a conjugated form and you also have free oligonucleotides, right? So free unbound little lines. Then the next step is to get rid of those little lines, right? To keep just the conjugated thing. And you see at the end, we're ending up with the conjugated antibody oligonucleotide complex. So is it important to understand all the stages and understand how all these information relates to the passage, or like how it relates to the diagram? Not at all. The point is, from this passage, we saw there's so many steps, so many different things. But when you look at the questions, there's often very key things that, as long as you can figure out where that's coming from and you can apply it back to the passage, none of the other stuff matters, right? So how did that feel?
Painful, as always.
Yeah.
Painful.
That was a tough passage.
Yeah, and I keep coming back to just confidence during this. I can completely understand a student gets to this point. It's like void. I'm voiding. I'm quitting. There's no point in me trying to do this. I have no clue what they're talking about. I didn't study this. I don't know anything. And it sucks. Like, it's just getting to this point, and I don't know. Obviously, we're doing this for educational purposes and hopefully helping some students get over their own insecurity. But I'm sitting here going, like, I don't know anything. I'm an idiot. Like, I can't do this.
I'm really sorry to hear that. And like, I hope that it's like, if anything, I've been able to show you that it's okay, one, to make the mistakes now. Two, a lot of the things that we talked about today are due to like content gaps. That's quite frankly it. Your strategy has been flawless. Your strategy has been excellent. The thought process and like eliminating answers, comparing answers, looking for like, the easy way out, that's actually the toughest part. That's actually the part that most students have a difficulty with. And that's the reason why most students see plateaus. So I definitely want to commend you to begin with, because like your thought process is there. The content, I'm going to tell you right now, you haven't seen this for like a
A long
long
time.
time, right?
A
The
long time.
fact that like you can still remember some of it is incredible. So that's all I'm saying, as in content can always be learned, but practice takes, like, the strategy takes time to refine, fine tune. And like I can see that in
Practice.
your
We
thought.
talk about practice.
Yeah, you're talking about practice, right? The strategy, I love seeing that, because if anything, that's a testament to how stable strategy becomes.
Yeah.
Because going back to when you wrote the MCAT, you probably taught yourself the same strategies, the same approaches, the same way to think about questions. And even to this day, even though the content has some gaps, all of the strategy is still there. The approach is
Well,
still there.
I scored an equivalent of a 502 back in the day, so I didn't have any good strategy.
No, but even a 502, I think most people think around a 500. They're like, oh, that's not a great score. But you need to remember that a 502 means you're in the top half of everyone who's trying to go to medical school. This isn't an average person. These are people who want to become doctors, who've studied hard. Like, a 500 is all, it means you're in the top half. It's a good score. It's something to be proud of. If you want to shoot higher, you have more goals, you want to set other things, you want to learn more strategies, absolutely. But don't ever look at a 502 and be like, wow, I'm dumb, or I'm not, like, it's tough stuff. So if anything, keep it up. Like, for our listeners at home, keep it up. Remember, like, if you have that feeling of, oh, I'm not smart enough, or you read a passage and you're like, I have no idea what's going on. The point isn't to know everything that's going on in the passage. The point is to remember the MCAT tests the same core concepts always. Always the same core concepts. They will dress it up. They'll put a clown costume on it for all I care. But they will show you things to throw you off. And just like we saw in that last passage, they will give you really tough passages with a lot of information. But if you take a step back and say, listen, I don't fully understand certain things, but I'm going to try the questions anyways, you're going to get rewarded for it. It's the same way when you go into your practice. I don't know all the content areas, but I'm still going to try the practice questions. I'm going to still try to refine my strategy. I'm still going to try my best. That mindset is going to be rewarded so much more than being like, I can't do it. I don't know how to do it. I just don't know. Change the mindset to, I just don't know yet. I just don't know how yet, right? Add that extra step, one strategy at a time. And before you know it, you'll look back and be like, I did that. So keep up your good work. And that's really all I got to say about that.